So we just looked at antiderivatives, and now we're going to look at antiderivatives integration to help us find areas under a curve bounded by the x-axis. So first thing that we want to look at is how we get that this is giving us the area under the curve. Basically, we're going to start out by taking shapes that we know to help us estimate the area under the curve. So mostly we're going to be using rectangles. And there's a couple ways that we can do this. I can use, it depends on how many rectangles they want. The more rectangles that we do, the more rectangles that we'll find the correct area. So for instance, if I had found the area for this curve that is given, actually, let's say if I just found the area of this rectangle in here, just one rectangle, it would give me an estimate of how much was under that curve. It would give me an overestimate, but it would give me an estimate of what was under that curve. If I decide to choose maybe, let's say, 2 rectangles instead. So it depends on where we want our endpoints or where our rectangle is going to stop. We're either going to have a left-hand endpoint or a right-hand endpoint or a midpoint. If I was to do a left-hand midpoint, let's say we wanted to break this down, and let's say that this was 6 here. We wanted to break this down into 2 separate rectangles to find the area. And if I use my left-hand endpoint, I could look at from here to here is 1 rectangle. And then from this point over here is the other rectangle. So this is going to give me a little bit better estimate of that area under the curve than before. Notice that we don't always know what these numbers are. So let's say that this was A and B. And so I want to figure out how many rectangles I'm going to have broken this into. And so if I look at the length of the rectangle, we are going to look at our endpoint of our interval AB. Let's say on AB. With n rectangles. Then this down in here, the length or width of each rectangle, we can find by B minus A divided by N. So you might see this in your book as triangle of X. So back over here, if I did what we had just did and used the numbers I had, I'd have 6 minus 0, all divided by 2 is 3. And so notice that you can see that each width in here is 3. And then notice that we know the height of each rectangle. The height of this first rectangle is going to be, in this case, f of a. In this case, f of 0, really. And my second triangle, this is actually f of a plus the length here. So we can find that area by summing each of those up. And so if we looked at the estimate in this case, with two rectangles, left-hand bound, we would look at the area of each, which would be 3 times f of a plus 3 times f of a plus the triangle of x, which in our case is really 3 times f of 0. F of 0 here, notice, is 7.5. Plus 3 times, this case right here is f of 3. F of 3, notice, is my y value here is 5 times 5. So this is equal to 22.5 plus 15, which gives me approximately 37.5. The thing is, the more rectangles that we subdivide this into, the better estimate that we're going to get. So notice if we had used the left-hand bound and split it up into 6 different ones. So from here to here. So hitting the graph on the left and then going over straight to here. We would have here to here, here to here. So this would even give us a better estimate of that area under the curve. So technically what we're gonna end up doing, we're gonna make those lengths or widths of those rectangles smaller and smaller, infinitesimally small. So basically the whole thing is just shaded and we have the exact area under the curve. So that's kind of the reasoning behind what we're going to be doing right now.